Hey, welcome everybody. My name is Amber Huffman. I'm really excited to welcome you. Google's very committed to open ecosystems, and so we're very pleased to host this breakfast. I'm going to belabor just 2 slides and then hand it off to the esteemed panelists. So I have the privilege of chairing the RISE consortium, so RISC-V software ecosystem that partners very closely with RISC-V International for how do we bring software forward more rapidly to support the RISC-V ecosystem. And so what we focus on in RISE is fostering the public, open source, and standards collaboration, establishing developer infrastructure like build farms and whatnot that many of you are involved in, and how do we activate the developer community through RFPs and the Developer Appreciation Program. And so if you want to learn more, you can check out the RISE website, but we'd be welcome to collaborate more. So the reason I started out this way is that the focus of our panel is really we're focusing on how do we look at software and hardware together and really have a great focus on software. So we have amazing esteemed panelists. Dave Patterson pretty much needs no introduction. Then we have Andrea Gallo, VP of Technology at RISC-V International, and Nathan Egge, who is at Google and also leading RISE TSC co-chair. And so I'm going to let each of our panelists introduce themselves in turn. So Dave, take it away.
I'm Dave Patterson. I don't need an introduction. I was Berkeley faculty for 40 years. When that got too hard and I needed a cushier job, I went to work in industry. And I've been at Google for the last 8 years. Up until recently, I was the vice chair of the RISC-V board of directors.
I'm Andrea Gallo. I'm vice president of technology at RISC-V. I joined 4 months ago. And so far it has been a blast. And before I spent quite a few years coordinating collaborative projects in another ISA. And before that, for many years, I was in the silicon side. I was at ST Microelectronics, working on multiple projects from telecom to smartphones up to a fellow position.
Yeah, and my name is Nathan Egge, and I'm an engineering manager at Google, leading our native tools and libraries team that does a bunch of compilers and tool chains. As Amber said, I'm also the co-chair of the RISE Technical Steering Committee, and I also chair the System Libraries Group, which has been doing a lot of software enablement for RISC-V. And prior to this, to Google, I spent about 15 years working on royalty-free open source multimedia, so a bunch of optimizations around audio and video formats, standardization.
So let's kick it off with Dave. So Dave, what are the top misconceptions for RISC-V related to software, and how can we address that?
The top, there's something on the website that says the top 10 fallacies. And I would say probably, I assume for software it'll be the fact that we allow customization means compatibility will be impossible. That's probably the top one. When Krista and Andrew and Jensep, came up with the ideas, they had the idea of it's going to be important in the future to be able to customize instruction sets. So the plan was from the beginning was customizable, but we understand software is king. It's got to be able to have a software platform that will run. So that was the plan from the very beginning. And the phrases that we use today is to have platforms that will specify for a particular market what instructions are included and what's binary compatible. So I think the confusion about customizability yet being able to have a stable software is probably the biggest fallacy out there.
Thanks, Dave. So Andrea, you're now 4 months in to your new role, and so what's your reflection about software and its importance for the RISC-V community?
I see 3 different kinds of software. One is enablement, one is reference stacked reference images, and one is workloads. The enablement, well, you need the low-level software, you need the BSP, the initialization, you need toolchain, but you also need a lot of hard work around testing for the ISA compliance and the simulators, the models. So that's all the enablement that is crucial to the ecosystem. Reference stacks is, to me, very important as part of the developer experience. you need to help the developers start designing their products immediately without having to rebuild the baseline. And workloads is a way to identify software bottlenecks that we can improve by evolutions of the ISA.
Thanks, Andrea. And a quick follow-up. How did you discover RISC-V?
I was 17. I had darker hair, more hair. I was a trainee, a summer trainee in a small company in the UK, Acorn Computers, and I was given a machine with the ARM2 processor and a pile of floppy disks, and I was asked to do some compatibility tests as a student. And they gave me a short paper to study this new ARM2 chip, and it was maybe a 15-page ISA manual and an article that explained that the story that inspired the ARM processor. And this was an article from 1985 from the chief architect there. And they said that they got inspired for the ARM1 design by the RISC-V papers from Berkeley. That's how I got exposed to RISC. That was many years ago.
And it all goes back to Dave. So Nathan, how do we build the community and enable the software ecosystem?
It's a great question. We spend a lot of time within the RISE System Libraries group thinking about how to build community around the software ecosystem. I think one surprising fact that maybe people don't immediately recognize is that quite a bit of software already builds and runs just fine on RISC-V. I mean, compilers work, libraries work. You can get Linux up and running, and about 98% of it just works out of the box. And so a lot of the discussion around building community is, what are the key areas that people are looking to do deployment in, and how can we help make sure that RISC-V performs well and is one of the best deployment targets for that work. And a lot of the ways that community is built is by digging in technically and saying, okay, what is the workload? How is it performing? What are the gaps? And a lot of times it's sort of surprising. The hardware is quite capable, and a lot of times really it's around making sure that you've connected the right people, the tooling is up to date, and that the gaps in terms of maybe capabilities are closed through some of the improvements to some of the software libraries.
Thanks, Nathan. So Dave, if you reflect back over the last 10 plus years or further, what would you have done differently? Like, knowing what you know now, technically, what are features you wish you would have foreseen, or what do you feel like that you were the oracle, or
Yeah.
what do you reflect back?
Well, first let me clarify that, in 1980s, I drove a lot of the ideas. And we actually did 4 RISC chips. We called the first one RISC-I and RISC-II, and we came up with other names for the next ones. One of the few things, if I had to go back in time and change, I would have changed it because it was a good brand name. It should have called it RISC-III and RISC-IV. So I told that story to Krista and Andrea and Jensip, and they said, oh, well then let's call it RISC-V. And I think because it's called RISC-V, I get too much credit. So you should probably ask that question to Krista. What does he regret? I'd say the thing, I'm going to talk at the keynote, looking back 10 years. But I don't know how we would have seen it, but we did not anticipate AI. And AI has had a huge impact on hardware and instruction set architecture. If we'd had a crystal ball, technically what we would have done is, instead of putting support for 128-bit floating point, we would have put in support for smaller floating point formats, anticipating that this was going to happen, and save outcode space for 16-bit, 8-bit, maybe even a 4-bit floating point. I don't know who's got a crystal ball that good, but if we look back, that's this giant opportunity, and it's one of RISC-V's strengths is that you can add custom instructions, which many people need to do for AI.
Thanks, Dave. And I think your crystal ball is still pretty good. So one thing, Andrea and Nathan, you guys have been talking about how software can help evolve hardware, and how it worked well with multimedia, kind of dovetailing a little bit with where Dave's going of if we imagined what hardware needed, how would we evolve software and other pieces, whether it's 8 bits and beyond. But what can you tell us the story of what's worked well?
To me, it's critical to run reference workloads. And the workloads, first of all, come from customer use cases. So it's real life. It's not just benchmarks or bottom-up analysis. It's the real use case, the real use of products out in the field. So by running workloads, complex software workloads, then you identify bottlenecks, maybe gaps in functionality, gaps in security, or maybe performance bottlenecks. That joint analysis drives the identification of opportunities for new ISA extensions, for new instructions that may be simple but will give you a tenfold speed up. So to me, that collaboration is critical. And I think, Nathan, can you share that golden example?
I can talk a little about it. So I mean, there's a couple places that this has come. I think multimedia is one of these neat examples where it is performance critical. It is on the software path for various reasons. And oftentimes, people ask about performance for these workloads, and performance improves kind of incrementally over time, right? People have an implementation, they deploy it, and they realize, okay, it could be a little bit better, and they chip away at this problem. And sometimes you'll find that the software doesn't have the right algorithm, and so you use the right algorithm, and now it's faster. Or sometimes you find that it doesn't map to the hardware, and then you do the right mapping to the hardware, and now it runs faster. And what's really neat about some of the work with RISC-V is we're kind of going down that path, and we're getting really close to finding out RISC-V does very well for these workloads, but there's just a couple small areas. And we've actually reached out to a number of communities who've put together sort of a wish list of here's a couple small instructions that will help with particular things that are kind of right there on the margins of being very specific to those workloads, and they will give a significant benefit because we're now down at the point where we're counting cycles and counting instructions. But the instruction set as it is actually quite capable, which is a really refreshing perspective looking at these performance critical workloads. And I think the part about community, there's this virtuous cycle, right? So we take the existing instruction set, we do this work and do analysis, then we feed back the, set of new features, new requirements, and then we work through how those will get deployed and rolled out. And I think the nice thing about RISC-V is that it has a natural mechanism for bringing these new extensions into an existing ecosystem in a way that's compatible.
So I'd love to open it up to audience questions after this next question. So if you have thoughts, please get ready to raise your hand for a mic to run around. So one thing that we've seen in other architectures is very much a vibrant software, hardware back and forth of what do we really need for evolving the hardware, for software, and this idea of co-design. Any thoughts on how we engage the software community and the hardware community to get that virtuous cycle going even better in RISC-V?
Why don't you go ahead?
Yeah, so I've got some thoughts. I mean, one thing that's always important is talking to people, like talking to your customers. Trying to understand the workloads is important, and so talking to people who are trying to deploy software, particularly either server workloads or client workloads, and knowing where their bottlenecks are. And I think when you start digging in and saying, okay, well, why is this not working as it was expected? Once you get past the surface level down into the technical details, you might realize, I'm not using this instruction set the right way, or there's a software concern that's not being addressed properly in hardware, and you can then kind of dig in and say, here is a joint solution that we can come to together that ends up being better than what either one of us could do by maybe working in isolation. So oftentimes the hardware folks don't exactly understand the software concerns, and certainly software folks don't necessarily understand what the limitations are of the hardware. So I think communication is a real key there.
As an example, I've been following the kernel mailing list for RISC-V, and recently I've been seeing the patches for shadow stacks, landing pads, pointer masking, and it's quite a learning curve when you have the specification for the ISA for these extensions, very important security extensions on one side, and then you see how just 3 lines of assembly do the magic. I think it's important to see both sides work together on both sides, and we should do this as early in the process as possible. There may be cases where, you know what, if that CSR was flicked in the bit fields in a different way, maybe on the software side we would avoid 2 or 3 mem copies that when you put them in a loop, it becomes huge.
And I think that I think kind of philosophically we're doing this new model where kind of for proprietary instruction sets, you know, they try and consult a lot of people, but then they announce it, and then everybody, all the software people hear about it, and then they complain. So because we have an open system, we can involve these people from all kinds of companies early in the process and have these conversations before we finalize it. So it may or may not take us longer. It's more obvious how long we take. It's less obvious with companies, but it's much more inclusive. So I think I'm hopeful that we'll end up with a much more satisfactory interface between hardware and software by being an open system.
And it's also unique when you see the collaboration between multiple companies in the RISC-V ecosystem that outside this room they are competitors. Here inside we're all engineers, we are somewhat all a bit geeks, and so we speak the same language and we enjoy collaborating together, and this is also unique.
Does anybody have a question they would like to ask? Redbeard.
So this question's for David. When you started your work, there was not a production Libre operating system. There was barely a Libre compiler. The kind of software ecosystem has really changed in terms of the collaboration and how work is done. What do you feel is still left to do in kind of evolving that story of changing how software and hardware can develop together?
Well, you know, it's one nice thing about being older is you can really do time travel backwards quickly. So let's go back to Berkeley in 1979, 1980. Berkeley Unix was the original open source operating system was dominating what we were doing at Berkeley, and we all used Berkeley Unix. It wasn't just a research project. It was code that was usable, and we got our work done on it. So for us, there was no question that the operating system was going to be an open operating system like Unix. So I'd say I wish I had spent maybe more time talking to my friends in operating systems about what their challenges were. An example, it would have been really easy for us to have done, make sure it was virtualizable. That wouldn't have been hard for us to do if we thought about it. But I'd say that would be one thing we could have done. I guess this is assuming that the operating system people at Berkeley were interested in virtual machines. but the idea was out there, and that's what would have been one we could have adopted. I thought operating systems would be a lot easier to port to hardware than they really were.
Other questions?
There's got to be more questions.
Don't be shy, or else I'll torture them.
Okay. Here's.
You know what I'm going to ask, right? You guys hosted by Google. So Google is the broker of the software. So we need the browser support on RISC-V. Desperately. So Chromium is stopping us selling the devices.
So the question is, when will Google support
Exactly. On the
RISC-V with Chromium?
Yes, officially.
I assume it's closer to you than me.
It's actually, Nathan, do you want to take that one, or would you like me to take it?
Why don't you go start it all?
It's not a technical question.
Totally understand the ask. You've seen the investment that Google's been making in Android for RISC-V, and we continue to make. And as customers ask for more support on RISC-V, that's the way typically that will come about.
Yeah, and I'll just add, I can't maybe give a better answer than that, but I will say that there is some technical work that's happening today, so it's not completely unworked on, but there is more work to be done there, and I do expect to see that coming in the future at some point.
But thanks for the request, and we'll take that back.
More questions? I saw hands though. Yeah.
It seems like there's a lot of really great conversations that are happening and collaborations around the core, and I'm wondering, like, where you see things going in terms of creating community and something similar around interconnects, accelerators, right? All the things that we need to actually build a computer system.
Maybe I can start. We have a working group around servers for RISC-V, and they're working on multiple levels. There's the performance side, the security side. You may see all those extensions like vector, matrix, hypervisor, and all the security. But then there's a next level. Those guys in the working group, they are standardizing some of the interfaces as part of the SoC. So they're working on a server SoC specification. And they're working on a boot requirement specification. And the next level that is ongoing is the server platform. That is closer to your question. So the companies, the members involved, are defining interfaces, software and hardware interfaces for common peripherals like timer, I/O, MMU, or important extensions like RAS. So that, I think, builds up above the ISA towards, I would stress the point that these are common interfaces that are not a competitive advantage between the various members, but are more of the common infrastructure work that makes sense to work on together.
Isn't there also an organization that's doing open source interconnect and accelerators and stuff like that? I can't think of the name right now.
Well, so we have UCIe, right, for the interconnect, and so we do have some of those interconnect standards, and how do we adopt those and really make those flourish? Next question. If another mic will help, we are happy to share if we need another runner.
So I guess the promise of the RISC-V was going into multiple applications for the future. And I believe that we are trying to penetrate into the data center as well as the mobile applications as well. When do you think we will be ready as a community to go explore those applications? If those applications are not fitting, do you think there will be another application that will give a chance for the RISC-V to be better or more popular?
Did you see Calissa's keynote yesterday? I think Calissa's keynote was projecting 30%, I'll make the numbers up, 30% of automotive, 30% of data centers, 30% of, what are the numbers?
Am I running faster? Getting very close to 30% on the data centers by 2031.
Yeah, but so it takes a while, for software, what I, kind of, when I started teaching, I would say it's called hardware because it's hard to change and software because it's easy to change. That proved not to be true. That proved not to be true. Hardware ended up being easier to change and software is hard to change. So there's this latency to migrate software, but it's hard for me to, if we get to 30% share of these major industries, that's pretty significant. I don't know if there's an industry that has no interest in RISC-V. That would be, I can't think of one.
Yeah, I'll just add, yesterday's big announcement of Ventana, talking about, being in the data center now. That was pretty big, and what we're doing in Inspire Semi with our compute accelerator, supercomputer cluster on a chip, it's coming, so pretty quick.
And the other day we announced a major milestone, that is the ratification of the RVA23 and RVB23 specification. That is critical because it's setting the bar high enough for OS vendors and manufacturers to produce parts that are when you want to run modern applications and operating systems in binary pre-built across a range of different devices from different providers, you need to have common standards. And the RVA 23 is setting the bar high enough, mandating critical extensions like support for virtualization hypervisors, support for vector. That means that the device manufacturer and the OS vendors can target an important set of features, rely on those for high-performing products. And so this is really a cornerstone for data center, for mobile, for automotive. And when you add additional extensions that, like maybe in the future Matrix, you can discover them at runtime. So this RVA 23 and RVB 23 is critical to get closer to being ready.
Yeah, and I think the point about latency is actually really important to recognize. You know, a lot of the performance that people talk about will come from using these extensions like Vector or the Matrix extension. And I think we've only really had hardware that does Vector available to software developers for about 12 months, right? And so that was a blocker for many projects to even accept patches, because they would need to see, you know, what are the gains by landing this patch? We're going to do some specialization for these particular workloads. Like, how do we know that this patch is both correct and performant? And so having more available hardware, and thanks to everybody in the crowd here for delivering, is the key to unlock those capabilities within these upstream software projects. And I think we're really starting to see people take that and be able to do work with them now in a way that they couldn't do under, say, emulation.
And this is part of the experiment we're doing too, right? By involving everybody and we reach consensus and announce it, then hardware gets built, right? What a company would do is not tell anybody about it and then announce the hardware with the thing so that it would be available. So that's why they go like, wow, you guys have been talking about this for years. How come there's no hardware? Well, that's the path we're on. If you want to have an open, you know, lingua franca for all for computing that everybody participates in the design, then there'll be this announcement phase, and then there's a latency to hardware, and you can't really make, you know, and my long-time experience with software people, as much as you try and beg them to get ready for something, nothing happens until the hardware shows up. Nothing happens until the hardware shows up.
Good morning, Mark Augustin. You were elaborating on my question already. So my question to you was, how can we accelerate the circle of the toolchain compiler from the conception of an architectural extension to the market penetration and usage of those features?
My guess is, if we could, you know, it's the challenge that all hardware designers face. How can we do hardware design faster? How can we go, you know, there's this possibility of doing shuttle runs where you get a small number of chips pretty inexpensively, relatively quickly. I don't know if that, I mean, I could imagine, you know, you could, if you had 200 chips quickly and you could put them into a cloud service, that might get hardware, the gap between announcement and hardware more quickly, something like that. I don't know if FPGAs run fast enough for software people to get excited about, but somehow shrinking that gap between when we announce something and when we have something that could run real code it's hard for me to think of something else, but maybe somebody else does.
Yeah, I mean, there's a couple things you can do. I mean, one of the things, and this is a critical part of the discussions we've been having around accelerating the software ecosystem within RISE, is how do we find those areas that need attention within the software ecosystem as quickly as possible. And if you kind of look at performance, it has sort of like a logarithmic fall off, right? Like, you don't have to optimize everything, you just have to go in and find the part that's, you know, in the inner loop on the critical path. And so one of the things you can hope to do is, if you, for example, I'll give you an anecdote. We were really curious to see what the state of compiler readiness was for vector length greater than 128, right? So we have this Banana Pi board, it's got 256 vector length. We tried to build an entire OS, you know, with C flags that turned it on. And we ended up finding a ton of compiler bugs, a ton of build system bugs, you know, things that just, people had hard-coded stuff to only do 128, and when you try to not do 128, tons of stuff broke. Filed a bunch of bugs, Jeff Law said, thank you very much. You surfaced early issues. We were able to address them now before we went down this path. It's an iterative cycle. And so I guess my answer is, please try out your workloads. Please try them even if they're under emulation. Please try them on available hardware even if it's not the exact hardware you would like to deploy. And please file bugs. People are listening and they can help when they know.
So last audience question, and then we'll do a wrap-up question for each of the panelists.
So maybe a bit self-serving here, but as you're talking about early software development, you haven't been talking a lot about virtual prototypes. And Andrea and Lenaro and Quimu, there are commercial tools for this. They may not be actually running it at real time, but if you run a lot in parallel, and you can because it's a simulation, they're actually very effective for early software development on porting, and actually for real workloads like AI, it's a great tool for that. So I'm just wondering, you haven't talked about that. Any comments about using software simulation as a development tool?
I think it was part of the comment to the previous question. To me, it's the QEMU work is fundamental, and I would like to see RISC-V on RISC-V, when you can develop native on cloud, as Dave was mentioning, when you have boards in the cloud and you can access them and you can do cloud native development there, and then the same would run on hardware. That allows you to break out a chip on multiple cores out there in the cloud and add emulation for new instructions or accelerators.
So Nathan, can you share how people can get more involved with directly in RISE or collaborate with RISE to move the software ecosystem faster? Any advice?
Yeah, so a couple things. So if you're a member of RISE, we've got a bunch of work groups that are quite active across all the different areas that you might care on the software ecosystem, from kernel and firmware to system libraries and infrastructure and things like that. Many of those groups have meetings that are open to the public or reach out to the public and bring in domain experts. One of the things that we've had a lot of success with is bringing in domain experts from things like high-performance computing, cloud computing. Multimedia was one, and we've also looked at other domain experts, maybe with server workloads, and have them talk about, here are the things that we are seeing when we're trying to deploy software, and here are the gaps. And that's super important because it lets us kind of connect the people that have the problems to the people that may be able to fix the problems. I would also encourage you to work directly with the upstream projects. There's no secret RISE software repos. We do everything upstream, and so I would encourage you to file your bugs directly upstream.
Andrea, can you share any parting wisdom of how the software community can work together, and also maybe from your experience of the course you took?
Yeah, I was making the example of myself looking at the kernel patches for some of the specifications. I think the other way around is also really important. As part of my ramp up and get into the role, I took a bunch of courses from the RISC-V website, and one is design a RISC-V CPU core. I know it sounds very, very easy because it's not a 3 or 15 out-of-order pipeline, and it's very simple, very basic. But when you move from the ISA to writing the Verilog for the decoder or the Verilog for the ALU, then you realize, then you appreciate the magic that Dave and Kirste, Andrew, Youngsu, then you realize the beauty of the ISA. You see how simple writing a decoder for those instructions. Then you realize why you don't have conditional execution, and you don't need it. As part of my learning curve, on purpose, I started from some C code and wrote it in ARM32 assembly and RISC-V assembly. And it was quite a great learning exercise. And then I realized I didn't use any conditional execution or any barrel shifter or updating the pointer, while there were other features like the compare and branch from RISC-V that are much, much more powerful. And well, initially I was surprised that I couldn't find those things that I was used to. But when you take those courses of designing the Verilog, the hardware part of a very simple RISC-V core, as simple as the course is, it's mind-blowing. You appreciate the beauty of their design. And so I encourage everyone to take that course.
So more appreciation of hardware by software people and more appreciation of software by hardware people is a virtuous cycle. So Dave, we're all super excited for your keynote later shortly. I loved hearing your words of wisdom, and I understand they're published. So can you tell people a little more about that and the 9 magic words?
Okay. All right.
Because this is important for life.
This will be, when I'm long gone, this will be my contribution to society. My wife's like, all right. So I'll take a minute to tell you the story. So a friend of mine, Catherine McCunley, at the end of her talk she gave like 10 years ago, she told her life story. And I said, well, that's really interesting. Why did you do that? She said, because grad students, when you give technical talks, think if you've had success, that you've had this silver spoon in your mouth and a perfectly smooth road, no bumps along the road, and it's important to let them know because they think they're having problems, nobody else but them, and to uplift them. So I started doing that, and then last year, at Timothy Pinkston at USC said, you should write it up. So I have. I've written it up, and it's called Life Lessons from My First Half Century. And if you go to the CACM website, it's there. You can look it up. But the story, one of my stories is the importance, one of my life lessons is looking for the positive opportunities. I think in engineering, there's so many things that could go wrong that if it's easy to give up. So you look for the positive opportunities. And my story is from my youth, is when I was 16, I was dating a girl and a few times, and I wanted to be, asked her to be exclusive, which at the time we said is called going steady, asked her to go steady. And she realized she's only 16, and so she said to me, well, Dave, you're such a nice guy, I don't know how to say no. To me, as a logical person, not a no sounded like a yes. So I said, great, and hugged her. And she's thinking, well, I'll let this guy down later, but we've been married 57 years. And she still may let me down, but not yet. So when you tell somebody you've been married 57 years, they say, what's the secret to your long relationship? And I used to say, people, remember your wedding vows? The vows people say are great, but nobody can remember their wedding vows. So instead I share the 9 magic words that we say after we've had a disagreement. And this is the key to a long relationship. It's 3 sentences. It starts I, you, I. Okay. I was wrong. You were right. I love you. There's no substitutions. You can't say I was wrong, you're right, you're a jerk. And many spouses, many couples think it applies to the other one, but it actually both of you need to say it. But if you say that, you also can have a very long relationship if you can remember those 9 magic words. That's right.
Thank you.
Thank you, Dave.